Okay, it's Sunday, and we're at the bottom of our man drive. Frosty is coming to say hello to Haley, but she's not home. Frosty, today we're supposed to work on the pentagon. How's that sound?
Okay, we're inside again, and we're going to talk about the geometry of a pentagon. Right, Frosty? That's right. You be a good boy now. Good boy. Okay, so the most pentagons that people will be used to will be this kind of pentagon. The house. This is a pentagon because it has 5 sides. It's not a regular pentagon because all of the angles are not equal to each other, and the sides may not be equal to each other. The pentagon that we're going to talk about is going to be called a regular pentagon. And a regular pentagon is hard to draw exactly, but it looks like this sort of a thing. And it's like the building down in Washington, D.C. is called the Pentagon because it's shaped like a pentagon. Now, the first thing that we're going to talk about is what is the angle in a pentagon. In a square, the angle is 90 degrees, or a right angle. But in a pentagon, it's not. It's more than 90 degrees. Now, one way to find out what it is to observe that since a pentagon has 5 sides, if you draw a pair of diagonals, you can cut it up into 3 triangles. In each triangle, the sum of the 3 angles in each triangle has to equal 180 degrees. Since there are 3 triangles, you have 180 times 3. That's 540. Now in a regular pentagon, all of the angles are the same on the inside. If they're all the same, they have to be equal to 540 divided by 5. That's equal to 108 degrees. That is the angle in the pentagon, 108. 108. They're all 108. Okay, so that gets us started. But now we want to learn more about a pentagon. And like how would you make one? It's pretty hard to make a pentagon. Now we know that what the angle is, but that doesn't help us to make it. So I'm going to draw the pentagon over again, and then we're going to talk about another part. Let's see. I don't draw a very good one. Okay, now what I'm going to draw is I'm going to draw the diagonals inside the pentagon. You've probably done this before. This is a 5-pointed star. And inside that 5-pointed star, you actually have a pentagon in the middle of it. And the 5-pointed star is also very symmetrical. So we know, we just learned about this whole angle up here is 108 degrees. All of them are 108 degrees. But one thing that we can learn now is we can look at an isosceles triangle. And you have to remember back from geometry, this would be an isosceles triangle. This side, and this base. The top is 108 degrees. These 2 angles have to be the same. And all 3 of these angles have to add to 180. And that makes this angle here 36 degrees. And also on the other side, 36 degrees. These small angles here. And because this is so symmetrical, you have 5 of these identical isosceles triangles, and it turns out that all of these are 36 degrees. And because the total is 108, that means the middle one is also 36 degrees. So there's a ton of 36-degree angles in this pentagon. And in particular, there's a very important triangle which has 36 degrees in it. It's this triangle right here. It's another isosceles triangle. It's a big one. It's got 36 degrees at the top, just like we talked about. Down at the bottom, the so-called base angle of this is 72 degrees on each side, because it's got actually two of these 36-degree angles in it that we just talked about. This is a triangle that's 72, 72, and 36. This is a very, very special triangle. And it shows up in the pentagon. And another pair of triangles that are very important that show up in this pentagon is this triangle right here, and then this triangle right here. Now these are very special because let's see if I can do this a certain way. I have to kind of keep erasing these angles so I can show you which is the exact angle I want to talk about. But if I talk about this angle, that's 36 degrees, like we talked about to start off. And this angle down here on this triangle is also 36 degrees. That makes this angle the very same 108 degrees that you have on each of the corners of the pentagon. And this is an isosceles triangle. This one is isosceles because these two angles are the same. Before I was telling you about isosceles triangles that were isosceles because the lengths were the same. But one thing that we learned from geometry is the properties of an isosceles triangle. If the two base angles are the same, then the two of the sides will be equal in length. Now, if this is a 180 degrees, and this is 36 degrees down here, on this one, this is a 72 degree again. So what we see here is we had this big triangle, the bigger one, that's 36, 72, 72. But then what we found was it was actually divided by one of these diagonals into a smaller 72, 72, 36, and also a smaller triangle, which was also isosceles, which was a 36, 36, 108. And this all just came out of a regular pentagon and using some very fundamental geometry on the properties of triangles. Now, where the golden ratio comes in here is the following. I'm going to call the length of this side of this isosceles triangle A. And I'm going to call this length of this isosceles triangle B. And I'm going to call this length of this is the base of this isosceles triangle. I'm going to call that C. Now, B plus C is equal to A because the length of this side of this isosceles triangle is the exact same as the length of the other side. Okay? And another thing is that this triangle is a similar triangle to this triangle. And this length B is also the length of this base, and it's the length of this side of this triangle. And that's because this was an isosceles triangle, so if this is B, that's B. This was another isosceles triangle, so if that's B, that's B. So this is very beautiful. And because of these isosceles triangles, on similar triangles, if you have two similar triangles, the ratio of corresponding sides are equal. one triangle might be bigger than the other one, but the ratio of corresponding sides are equal. So what I'm going to say is the ratio of A to B, okay, that's the ratio of this longer side of this triangle, is going to be equal to the ratio of B to C. And that's because B is the longer side of the 72, 72, 36 triangle, and C is the base. So we can write that like this. A over B equals B over C. But also, we know that B plus C is equal to A. So this shows that a certain length A can be divided at a certain point into two smaller sections such that the ratio of the total length, which is called A here, to the larger of the two that you've divided it, which is B, is equal to the ratio of the larger to the smaller. The smaller and the original are called the extreme lengths because one is the smallest and one is the largest. The length B is called the mean. It's in between them. This is called dividing the line into extreme and mean ratios. It's dividing it so that the ratio between the entire line to the larger is equal to the ratio between the larger side and the smaller of the two segments. And this happens naturally inside of a pentagon. And this type of division, which was called by the Greeks as the extreme and mean ratio, is nowadays called the golden ratio. It's the golden ratio. And there's a way to solve for it, exactly what that ratio is, just using algebra. And the way that we can do that is if we just call, now for the time being, I'm just going to change this now, and I'm going to call B x. I'm going to call C 1. This whole length is 1 plus x. I'm going to call x the golden ratio because it's the ratio of this to that. And if I call that just 1, that length is actually going to come out in the units that I'm using as the golden ratio. Now the formula that I had was that the ratio of 1 plus x, that's the entire length, to the larger of the two, which is x, is equal to the ratio of x to 1. And that's the exact same as what I have over here, which is to say that the original length of the line to the larger side is the ratio of the larger to the smaller. But here I'm doing it in a way where I can just solve for what is the ratio between these. This turns out to be a quadratic equation, which is relatively easy solved because we know the quadratic formula. This just becomes, by cross multiplying, x squared is equal to x plus 1. And when you solve that using the quadratic formula, you get that x is equal to 1 plus square root of 5 divided by 2. And that turns out to be the ratio in a pentagon, a regular pentagon. That is the ratio between the base, or one of the sides, and one of these diagonals. They're in a golden ratio. It's also the ratio of this one of these diagonals in the way that it is cut by another diagonal. It's cut into a golden ratio. It turns out to be about 1.6. Some people think that the Greeks built the Parthenon so that it would be in the ratio of this number because they thought it was special, but actually mostly I think that's all been debunked. The Greeks never called this the golden ratio, and when they actually looked at the dimensions of the Parthenon, it's not really exact. It might be just close. But so there's a lot of stuff out there about the golden ratio, but this is just the mathematics of the pentagon. And this shows you how this ratio is important in constructing a pentagon. If you can construct two lines that have the ratio of this, one of them you can make to be the diagonal of this triangle. The other one you can make to be the base. Then it's possible to construct a regular pentagon with compass and straight edge. And that's really what the Greeks were really like to do.